Lesson 7-2, Hooke's Law and Simple Harmonic Motion. Consider a mass hung from a spring. You have it there, and then you let it go, and the mass pulls it down. Oh, but then the spring pulls it back up, and it goes up and down and up and down. If it was to just hang, it'd hang in the middle at equilibrium. If you pulled it down or pushed it up and released it, it would bounce up and down. So it'd be up and then down to, this is equilibrium here in the middle. So it's pushed up, it go down, and then it go down below equilibrium, and the spring pulls it up. It gets too high, and the gravity pulls it down, stretches the spring out. Then the spring pulls it back up, and so on. Looks like we get a sine curve if we look at its position versus time. We had Hooke's law back in the unit on forces. The force due to a spring was negative kx, where k was the spring constant, and x was the distance it was stretched. So F is the restoring force, wanting the force to pull it back towards equilibrium. X is the distance it's displaced, and K is the spring constant. The force will pull the mass back towards equilibrium, but as the mass gets to equilibrium, it has momentum. So then it carries on past the equilibrium point until the spring force is strong enough and pushes it back the other way. And that continues back and forth, back and forth. Using calculus, we can take that force equation for Hooke's law and find the energy in Hooke's law. Because remember, work or energy was force times distance. The force changes with distance, so it's a complicated calculus. And we end up with the potential energy for spring or elastic. The EL's for elastic. Potential energy is 1/2 kx squared. Let's do an example. A Nerf dart gun uses a spring to launch a dart. If it takes 24 newtons of force to compress the spring 6 centimeters, what is the spring constant? And how much potential energy does it contain? Well, we're told a force and a displacement, which if we put it into meters, it'd be 0.06 meters. The force is always the opposite direction as the displacement. If you're from equilibrium, if you're below it, if the displacement is down, the force is going up. For above, so the displacement is positive, the force is down. So one of these has to be negative, so we're going to let the displacement be negative. We're looking for the spring constant. So we can use Hooke's law. F equals negative kx. So if we have 24 newtons, and our x is negative 0.06 meters, k is 400 newtons per meter. To get the potential energy, it's 1/2 kx squared. So it's 1/2 400 newtons per meter that we just found. And our displacement was negative 0.06 meters squared. Which gives 0.72 joules of energy. On a string, if one part of the string is pulled up, so that you get a wave pull. So here's a string. We pull this part up. Then the next piece of string will be pulled up. So that little bit is going to pull up this next little bit. And then that's going to pull up the next little bit of string, and then that'll pull up the next little bit of string. After the pulse passes, the string moves back down to the equilibrium position due to Hooke's law. So the force pulls it back down. If you apply more force, the quicker the string accelerates back and forth, and the wave travels. So if we have more force, there's more force for Hooke's law, and it's going to have more acceleration. So to find the speed of a wave on a string, it depends on the medium, so that depends on the string in this case, what type of string it is, how big it is, and the tension of the string, the linear density, that is how much mass it is per length, so in other words, how heavy the string is. And so the speed of a wave on a string is the square root of the tension per the linear density. This brings us to the idea of simple harmonic motion, which is motion that regularly repeats. So it goes up and down and up and down and up and down. The frequency turns out to be independent of the amplitude. So the up and down motion is independent of the amplitude, because if we stretch that out higher, there's going to be more restoring force and thus more acceleration. So the frequency and amplitude are not related. The period is 2 pi times the square root of the mass over the spring constant. So this is still, think of the mass on the end of a spring. So this is our mass, and then we have the K for the spring constant. Frequency is the reciprocal of that. If we had a graph of the position versus time, a simple harmonic motion, we get a wave. Looks like a sine wave as it goes up and down. So think of a point on a string some distance from the origin. We want to know the vertical displacement of the particle at any given time. If the wave repeats, it'll look like a sine graph or cosine graph. They happen to use cosine in our book. Y equals a cosine of 2 pi t over the period. But if we look at one point on the wave, it goes down and then back up, down and then back up, down and back up, down and up. And as it passes along, we have that nice sine or cosine wave and graph. A wave has an amplitude of 1.5 centimeters and a speed of 20 meters per second and a frequency of 100 hertz. Write the equation of the wave position of the wave. All right, so if I go to that last one, it was y equals a cosine 2 pi t over the period. A is the amplitude, so that would be 0.015 meters if we change it to meters. And t is time, that's a variable. Capital T, though, is the period. So frequency and period are reciprocals. So if the frequency is 100, then the period is 1 over 100, or 0.01 seconds. Okay. We could simplify now. 2 divided by the 0.01 seconds is 200 pi t. And now we have a function that'll give us the position of the wave at any given time.